Welcome back, truth seekers and curious minds, to what is the channel where we unravel the universe's biggest questions, one perfectly explainable concept at a time. Today, we're diving headfirst into a topic that sounds like it was dreamt up by a particularly disheveled philosophy student. After 3 consecutive all-nighters, chaos theory, and more specifically, why those seemingly insignificant, teeny-tiny little things matter so much. Today's question: what is chaos theory, and why small things matter so much? Now, before you conjure images of someone trying to organize a sock drawer after a particularly strong earthquake, let's clear something up. When scientists talk about chaos, they're not talking about your kitchen counter after a week of takeout. They're not talking about the sheer pandemonium of a toddler's birthday party. No. While those are certainly chaotic in the everyday sense, chaos theory is far more elegant, far more mathematical, and arguably far more terrifying. At its heart, chaos theory deals with deterministic systems that exhibit what's called sensitive dependence on initial conditions. Yeah, I know, it sounds like a secret handshake among very well-dressed mathematicians, but let's break it down. Imagine a game of billiards. You hit the cue ball, it strikes another, and they scatter across the table. If you hit that cue ball exactly the same way twice, you'd expect the same outcome, right? Every ball ending up in the same pocket, maybe even the same scratch on the felt. Common sense. But chaos theory whispers, not quite. If you were to repeat that shot, even with the most advanced robotic arm, the tiniest, practically imperceptible difference, a single atom's displacement in the air, a microscopic tremor from a truck passing outside, a stray thought about what to have for dinner that slightly tenses your arm, could, over time, lead to a completely different result. One ball might sink, another might remain on the table. The future, in this system, becomes profoundly, gloriously, maddeningly unpredictable. This isn't about randomness. That's a crucial distinction. The billiard balls are still following the laws of physics. They're still bouncing off each other and the cushions exactly as they should. The system is entirely deterministic. Given the exact initial conditions, you could predict the outcome. The problem is, we can never measure those initial conditions with perfect precision. There's always some infinitesimal bit of uncertainty, and in a chaotic system, that uncertainty gets amplified, magnified, and blown out of proportion faster than a rumor about a new office coffee machine. And this, my friends, brings us to the most famous poster child of chaos theory, the butterfly effect. Our story takes us back to the early 1960s, to a brilliant meteorologist named Edward Lorenz. He was using one of the earliest computers to simulate weather patterns. Imagine a machine the size of a small car, doing calculations you could now perform on your phone, while simultaneously ordering pizza and composing a sonnet. Lorenz had a model. He had input numbers representing temperature, pressure, wind speed, and watched as his virtual weather system evolved. One day, he wanted to rerun a simulation. Instead of starting from the very beginning, he decided to save time by inputting numbers from a point midway through a previous run. The original sequence of numbers he'd used was something like 0.5061 to 7. But when he typed them in, he rounded them to 0.506. A tiny difference, right? A mere flicker of a decimal point. A rounding error so small, most of us wouldn't even blink an eye. He went to grab a coffee, probably thinking about the impending glory of perfectly predicted weather. But when he returned, instead of seeing a continuation of his previous weather pattern, he saw something entirely different. The new simulation started off similar, but over time, it diverged wildly. It was like watching 2 identical twins walk into a room, only for one to suddenly sprout a third eye and start juggling flaming chainsaws. They were not the same at all. That minuscule difference, that 0.0001 to 7, was enough to completely alter the simulated weather system's future. This led Lorenz to famously quip about a butterfly flapping its wings in Brazil, potentially setting off a tornado in Texas. And thus, the butterfly effect was born. It's not about a magical butterfly literally causing a tornado. It's about an incredibly small, almost imperceptible change in one part of a complex system. Being able to trigger a cascade of events that ultimately leads to large-scale, unpredictable consequences elsewhere. It's a powerful and, frankly, humbling concept. It tells us why long-range weather forecasting is such a nightmare. We can get pretty good at predicting tomorrow, maybe even the day after, but a week out, a month, forget about it. The atmosphere is a massive, incredibly complex, chaotic system. Every gust of wind, every dewdrop, every slightly confused butterfly flapping its wings, constitutes a tiny initial condition that we cannot perfectly measure or account for. And it's not just the weather. Chaos theory pops up everywhere. In population dynamics, explaining why predator-prey numbers can swing wildly and unpredictably. In the way water flows, creating incredibly intricate and never-repeating patterns of turbulence. Even in the human heart, where chaotic dynamics can be both a sign of health and, terrifyingly, a precursor to cardiac arrest. Think about your own life for a moment. Ever wake up late because you hit snooze one extra time, missed your usual bus, ended up taking a different route? Overheard a conversation from strangers that sparked an idea, which led you to a new hobby, which connected you to a person who eventually became your business partner. That extra 5 minutes of sleep, that was your personal butterfly. We like to think we're in control, meticulously planning our futures, but the universe, in its infinite wisdom and chaotic glory, often has other plans. And those plans can hinge on the most insignificant seeming choices or events. So, why do small things matter so much? Because in chaotic systems, the relationship between cause and effect isn't linear. It's not a leads to B leads to C. It's more like a leads to a microscopic ripple which bounces off D, interacts with F in a way we couldn't predict, causing an entirely new pattern of E before finally manifesting as Z. The system is incredibly interconnected. And because we can never measure everything perfectly, we can never perfectly predict its long-term behavior. It is a testament to the fact that the universe is far more intricate and sensitive than we often give it credit for. It forces us to confront the limits of our knowledge and our ability to control. It means that the small acts of kindness you perform, the tiny choices you make, or even the accidental spill of coffee on your keyboard might, in a bizarre and unforeseeable chain of events, set off a ripple that changes something profound down the line. So, the next time you dismiss something as just a small detail, remember the butterfly. Remember Edward Lorenz and his rounded numbers. Remember that sometimes the smallest tweak, the most minor deviation, can lead to entirely new worlds of possibility, or indeed, complete and utter, albeit deterministic, chaos. And that, my friends, is what is chaos theory and why small things matter so much. It's a humbling thought, isn't it? A reminder that we are all part of an incredibly complex, sensitive, and unpredictable dance. If you found this exploration of sensitive dependence on initial conditions as fascinating as a perfectly organized sock drawer, then please give us a thumbs up. Don't forget to hit that subscribe button and ring the notification bell so you never miss another deep dive into the universe's most mind-bending concepts. What other topics make you ponder the unpredictable nature of reality? Let us know in the comments below. Until next time, keep asking, what is